Of course, there are a lot of other applications of differential equations besides kinematics, kinematics being the study of motion. A couple that we're going to look at are flow and growth. It always is helpful to remind yourself that the rate of change is equal to your input rate minus your output rate, and that will help keep you in track. So for example, looking at this harvesting model. So if we have a simple model, this is a simple model for a harvested resource, such as timber or fish, something that you're going to harvest, and it assumes a competition between the harvesting and the natural growth of the resource. And this process may be described by the equation P prime of t equals R times P of t minus H. So H is your harvesting rate, right? That's your output rate. And R times P of t, well, R is your natural growth rate, and P of t is the amount of the resource at time t. So if you take your natural growth rate times how much of it there is, that will get you your input rate. So it's input rate minus output rate, and that will get you your rate of change in the growth of whatever this particular item is, like timber or fish or something like that. So suppose that we are given constants P0, R, and H. So in other words, we're assuming that the rate of natural growth is constant, the harvesting rate is constant, and P0, the initial amount that you were given, is constant. Verify that this function, P of t equals P0 minus H over R times e to the RT plus H over R, satisfies this harvesting model above. All right, well, let's start by taking the derivative because we can see that this involves the derivative. So let's do that. P prime of t. Now remember, the only variable in all of this is that t right there. Right? That's the only variable. Everything else is constant. And of course, the derivative of e to the something is e to the something multiplied by the derivative of the inside. So it'll be P0 minus H over R e to the RT times R. And then the derivative of H over R would be 0 because that's constant, right? So you're assuming all three of these are constants. And then this is chain rule right here. All right, well, let's put the R in there. I mean, you might as well. So that's P0 times R minus H e to the RT. Wasn't strictly necessary, but it might make things a little easier later. All right, now let's see if I can get it to match the right side. So this is P prime of t, so this is the left side of the equation. So now I want to play with the right side and see if I can get it to be equal to that. So the right side of the equation is R times P of t minus H. That would be R times, and then P of t was given, of course. So that would be P0 minus H over R, e to the RT plus H over R, minus, all of that. All of that goes in there for P of t, minus H. So this whole thing was P of t that was given. Here, let me highlight it for you. This is P of t, so that's right there. It's P of t. All right, now let's distribute R into each of these pieces. So R going to this H over R will just make H. R going into this will make it P0R minus H, e to the RT plus H minus H, which is in fact P0R minus H, e to the RT. So this is the right side. And notice they're the same. This left side and this right side are equal. Sorry. And thus we have verified that this solution, or excuse me, this P of t does in fact satisfy the equation that P prime is equal to R P of t minus H. because I got the two sides of the equation to be equal to each other. Now, let's graph it for a given P0 and a given R. So we're going to let P0, which is our initial quantity, be equal to 1,000. And we'll let R be our growth rate, our natural growth rate. And we graphed the solutions for harvesting rates 50, 90, 130, and 170. And you can see I've graphed them here for us. I did it in Desmos, so you can also see them there as well. So let me grab it. And there you can see them. So we have the 50 up at the top, then we have 70, 90, 130, and 170. There they are. So we've graphed the solutions. Describe and interpret the four curves. Well, that's the interesting part. And you can see that if the harvesting rate is smaller, like 50 or 90, then the amount of the population will actually continue to grow, right here with the 90 and the 50. But if the harvesting rate is 130 or 170, then the population will go down. And matter of fact, with 170, it will collapse and not exist anymore after 8.83 for your time unit. So how much of this resource there is greatly depends on what the harvesting rate is. So let me write that up for part B. Actually, I'll write it and I'll be right back. So you can see how much of the resource exists at time t, because this is the P of t. This is the amount that's in the wild, if you will. So how much there is of it depends greatly on the harvesting rate h. If h is small, so say in our example like 50 or 90, example, e.g. 50 or 90, then the quantity will grow over time. If h is large, in our case 130 or 170, then the quantity will shrink. And you'll notice with 170, it actually collapses. You've driven this to extinction, whatever this is. The item is no longer available. At around 9. We don't know what unit this is, so I'm going to guess this is years or something like that. Now for part C, they want to know what value of h gives a constant value of p for all t. All right, so we started off at 1,000, so that would be where we want to stay constant at. So the constant rate we want is right there. So if we look at letter C, it would be P of t equals, and then our initial amount was 1,000 minus h, which I don't know, but over r. So h over 0.1, because that's my r value, e to the 0.1 t plus h over 0.1, which is the same thing as saying 1,000 minus 10h, because division by 0.1 is the same thing as multiplying by 10, e to the 0.1 t plus 10h. Now this will stay constant if this term right here would be equal to 0, because then it would stay constant no matter what value of t, because this is the part that has t in it. So in order to make this constant, this piece must equal 0. So then we're going to set that equal to 0. So set 1,000 minus 10h equal to 0. And then that would mean that 1,000 equals 10h. So h is equal to 100. So that would be the harvesting rate that would keep it at at a constant. And let's see if Desmos agrees with us. So let me go here. I'm going to turn off my graph for part B. I guess I can leave it on. It doesn't really matter. But I'm going to put in a graph here, and I'm going to let H go to 100, what we just said would make it constant. Whoop. There it is. And look at that. It's flat. Right? There's H equals 100. That's my equilibrium state. So indeed, Desmos backs us up. And I could draw that on the picture on the page. Back to here. So for part C, we figured out if H is equal to 100, it keeps it constant. And of course, you can see the farther away from you are from 100 down here, right, as 50, it grows quite a bit. If it's 90, which is close to 100, it's really kind of flat. 170, which is far away from 100, makes the population plummet.